We're going to look at hypothesis tests of the population mean when the population standard deviation, sigma, is known. So just like in confidence intervals, when we're doing hypothesis tests about the population mean, we have a sigma known case and a sigma unknown case. Now there are three forms of hypothesis tests: lower tail, upper tail, and two-tail. The steps you take in a hypothesis test depend on which form of the hypothesis test you're doing. So we're going to start by looking at lower tail tests. So remember, lower tail tests look like this. The null hypothesis is that the population mean is greater than or equal to some value mu naught, and the alternative hypothesis is that the population mean is less than that value mu naught. So the example we're going to look at in our lower tail test is mu is greater than or equal to 20 in the null hypothesis, and mu is less than 20 in the alternative. So our mu naught here is 20. The sample size is 50. The sample mean is 19.4. The population standard deviation is 2, and the level of significance alpha is 0.05. So the first step in a hypothesis test is to calculate the test statistic. And this is always the first step in a hypothesis test. And the formula for the test statistic is going to be the same regardless of what form the hypothesis test takes. So if it's lower tail, upper tail, or two-tail, as long as sigma is known, the formula is going to be z equals x bar minus mu naught over sigma divided by the square root of n. Now, since our sample mean follows a normal distribution, and we're subtracting the mean of the sample mean, which is the population mean, and dividing by its standard deviation, sigma over root n, then our test statistic z is going to have a standard normal, or z, distribution. So our test statistic is written z because it follows a z distribution. So let's calculate the test statistic in our example here. So we have z is equal to x bar, which is 19.4, minus mu naught, which is 20, divided by sigma over the square root of n, and we get negative 2.12 for our test statistic. Now, there are two different ways that we can use our test statistic. We can use our test statistic using the p-value approach or with the critical value approach. In the p-value approach, we calculate something called a p-value. Now, the p in p-value stands for probability. The p-value in a lower tail test is the probability of getting a value for the test statistic as small as or smaller than that provided by the sample. So the key here, what makes this the p-value for a lower-tailed test is this part here, as small as or smaller. So our p-value is the probability of getting a test statistic that's as small as or smaller than the value provided by the sample. Now, the value provided by the sample is negative 2.12. So our p-value is the probability of getting a test statistic that's less than or equal to negative 2.12. Now our test statistic follows a standard normal or z distribution so our p-value is the area to the left of negative 2.12 under a z distribution. So what we want to do here is we want to use our z-table. We want to look at the negative side and look for negative 2.12. So we match up negative 2.1 with 0.02. And we get the p-value is 0.017. So this area here to the left of negative 2.12, which is our p-value, is equal to 0.0170. Now we have to use the rejection rule for the p-value, which says to reject the null if the p-value is less than or equal to our level of significance, alpha. So our p-value here is 0.017, which is less than our alpha, which is 0.05. So our conclusion is to reject the null because it satisfies our rejection rule. So in this example, we reject the null, which means we accept the alternative. So we conclude that the population mean is less than 20. Now, the second way of using our test statistic to conduct the hypothesis test is to use the critical value approach. In the critical value approach, we calculate something called a critical value. Now, in a lower tail test, when sigma is known, we write our critical value as negative z alpha. And negative z alpha is the value of the test statistic corresponding to an area of alpha in the lower tail of the sampling distribution of the test statistic. Now this definition is a bit long. We can simplify it quite a bit. Now, when we say value of the test statistic, well, the test statistic follows a z distribution. So what we're really saying here is the z-value. So we're looking for the z-value corresponding to an area of alpha in the lower tail of the sampling distribution of the test statistic. Now again, when we say sampling distribution of the test statistic, our test statistic follows a z-distribution. So what we're really saying here is the z-distribution. So our critical value is the z-value corresponding to an area of alpha in the lower tail of the z-distribution. That's what this definition is really saying. Now what makes this the critical value for a lower tail test is obviously this part. That's an area of alpha in the lower tail. So to find our critical value, we want to find the z-value that gives an area of alpha, and in our example, alpha is equal to 0.05, in the lower tail of the z-distribution. So let's look at our z-table, and we're looking for an area of 0.05. So here we have 0.0505. So this corresponds to negative 1.6. And 0.04. So our critical value is negative 1.64. Now notice next to 0.0505 we have 0.0495, which is also very close to 0.05. So we could also use the critical value of negative 1.65 in this example. It doesn't make a difference which one you use, both would be okay. So our critical value that we're going to use is negative 1.64. Now the rejection rule for the critical value for a lower tail test says that we reject the null if our test statistic is less than or equal to our critical value. So in other words, if our test statistic is in this region here, in the shaded region, we reject the null. Now, if it's in this region here, the region that's not shaded, we do not reject the null. So our test statistic that we calculated earlier is negative 2.12. So our test statistic is less than our critical value of negative 1.64. So our conclusion is, again, to reject the null. Now, notice that our conclusion for the critical value approach was the same as our conclusion for the p-value approach. Now, this should always be the case unless you made a mistake. If the p-value approach says we should reject a null, the critical value approach should also say we should reject a null. If the p-value approach says do not reject a null, the critical value approach should also say do not reject a null.